You're listening to Strange by Nature, your guide to the strange, weird, unbelievable, and improbable wonders of the natural world.
Hello, everyone. Thanks for being here today. I am Kirk Mona, and I am joined today by Rachel Ginza and Victoria Thompson. We are all professional naturalists who together have scoured the world for weird and wonderful wonders just to please your mammalian brain's desire for novelty. Isn't that nice? Let's do this.
Hey, everybody. So for this week, I have a simple tale of a not so simple plant. And strangely, this plant is most often found growing in places that are not the best growing conditions, but rather the worst for other plants. And we actually see this a lot in nature. It's like any plant can grow in perfect, lovely conditions, right?
Right.
But if you're in a really good, lovely spot, there's a lot of competition, for those lovely, perfect spots. So what about the less than perfect spots? And you may not grow quite as well in one of those less than perfect spots, but if there's less competition, then you can actually thrive. So this week I'm talking about a plant called, now I get to say our favorite part is when we try to say these scientific names. It's a Brassica oleracea. All right?
Brassica.
And
wait, say it again.
Oleracea?
Yeah, Brassica oleracea.
Yeah.
Okay.
So it can grow under a number of conditions, but it has a weakness. It doesn't like competition.
Okay.
Right, like we talked about. So you could grow it in a beautiful, lovely, growing conditions, but pretty much everything else can also grow in these conditions too. So there's just too much competition for this plant.
Right.
And it has a secret weapon, though.
Does it?
It is highly resistant to salt and lime.
Lime?
And those are two things that a lot of plants don't really like.
Yeah.
Right? And those are both common on limestone cliffs near the sea. And that's where we find this plant growing in the wild. So it grows in a number of places, but the one I was able to find sort of most commonly cited is that it grows along the limestone cliffs on both sides of the English Channel.
Okay.
So if you can kind of picture, like the big white cliffs and everything, that's where you'd find this plant.
Right.
And scientists who've studied wild populations, though, have noticed something about the genetics of this plant. They're a bit sus.
Oh, are they? Are they? Are you getting with the youth there, Kirk?
It seems like they may not. Well, like there may not really be any truly wild examples of this plant left in the wild, because what is found in the wild is actually probably more appropriately called a feral plant rather than a wild plant.
Okay.
You see,
like
this is a plant. This is a plant that has been cultivated by humans for thousands of years. And the earliest evidence for the cultivation of this plant goes back to about 2000 BCE. Whoa. So, yeah pretty far back, about 4,000 years. So one of the older names for this member of this plant, which, by the way, is a member of the mustard family. It's not mustard like we would, that yellow stuff comes in a tube. But there's that whole plant of... family of plants.
Yeah.
And this plant, it had a name. People called it colewort.
Colewort?
And I know that doesn't sound real tasty. Like, want some colewort for dinner?
Okay,
so any examples?
But Kirk, lumberjacks used to drink something called dishwater with sand. Like, who knows?
Right, so maybe, if that's what you grew up with, it would seem totally normal. But examples in the wild are like the descendants of these long since forgotten gardens that were cultivated. So possibly even hundreds or thousands of years ago. So colewort was cultivated and grown from wild plants thousands of years ago, but you may not realize it, it's still cultivated today. And you might be thinking, hold on, I've never eaten colewort. But I'm pretty sure everyone listening actually has. Yeah. So today we call it kale. So the kale we have today is a descendant of the original wild plants.
Okay.
And they're not a new species, mind you. The kale we eat today is just a cultivar or a variety of Brassica oleracea. And there's dozens of varieties of kale, and they're all because farmers decided to focus on growing plants with like the biggest and tastiest leaves of this wild, colewort that they were finding.
Right.
But something really interesting happened pretty early on in cultivation. Some farmers decided to focus on really developing the terminal leaf buds and trying to see how big they could get those instead of the leaves. And it turns out you can get them to be pretty big.
Yeah, you can.
And we end up with a plant called cabbage.
Yes.
Yes,
so
we do.
cabbage is the same plant as kale, and cabbage goes back at least 1,000 BCE, so 3,000 years ago. And people have gotten a little carried away.
People have gotten
with
very
breeding
excited.
This plant. There's currently over 400 varieties of cabbage grown in the world. And they all came from
insane.
this one
Just
plant.
cabbage, not including the kale varieties.
Right, just the cabbages
cabbage.
alone. There's 400 of those, and then there's many varieties of kale. So it's pretty wild. It seems like you can pretty much get every color of the rainbow that you would like out of this plant. So about 2,000 years ago, we find another variety of this plant showing up, and it looks a bit like kale, but these leaves are smoother and taste different. And it turns out it grows in more places as well. And you've probably heard of them. We also get collard greens. So collard greens are technically the same plant as cabbage and kale.
Yep.
In fact, they believe the word collards actually harkens back to that original name for the plant, colewort. And they're kind of a similar sounding word.
That's
Okay.
probably just kale.
Yeah, probably. So we got kale and collards by focusing on the leaves and cabbage by breeding for the terminal leaf bud. People were wondering, what else can we do with this plant? Well, it turns out
Let's find out.
a lot. In the 1200s, farmers were looking at the lateral leaf bud as opposed to the terminal leaf bud. So lateral leaf buds are the ones on the side as opposed to the one up on top. And they're thinking, hey, I bet we could mess with those.
This seems fun.
I think I know what
after
we're going to wind up with here.
Yeah, me
lots
too.
of selective breeding, they came up with a variety of brassica with a tall, thick stem and giant, tightly packed leaf buds growing up the side. And we know those leaf buds today as
Brussels sprouts.
Brussels sprouts. That's right. The same plant. It's the same plant, everybody. So, not to be outdone there, in the 1500s, farmers decided they wanted to focus on the flowers
Yeah, the
instead
flowers
of the
are
leaves.
feeling left
already,
out here.
Yeah, we already been messing with everything else. How about those flowers? So they selectively bred kale with huge flower buds and created a plant we today call broccoli.
Broccoli.
So, yep,
Hey.
broccoli is also the exact same plant. Now, incidentally, there are many kinds of broccoli out there. I couldn't find good data on like how many varieties have been created, but my absolute favorite is the Romanesco broccoli. You
Oh,
ever seen
yeah,
this
that's
before?
so cool.
I don't think I
So
have, yeah.
it's the flower heads, instead of being like the little miniature trees that we think about, they actually grow in fractal self-repeating spirals.
Oh, that's cool.
It is utterly bizarre and really beautiful. It's so bizarre, it was actually used in Star Wars The Force Awakens. It's one of the strange looking foods served at Maz's castle. Look carefully. They've taken like an apple and cut it in half and completely scooped it out. So it's the shell of an apple. And they shoved like some Romanesco broccoli and some other little like sprigs of plants in there. And that was like this exotic alien food. No, it's just one more version of this wild plant.
That's
So
awesome.
back to brassica. This tinkering wasn't just going on in Europe. This little plant had by now spread around the world, and people kept on breeding new varieties. So we're not exactly sure when, but farmers in Southeast Asia began to experiment with it and focused on making the stem big and bulbous, and we ended up with kohlrabi, which is also the same plant. We know
We're
it
up
was
to
likely
5.
sometime before the 1500s, because that's when authors in Italy first noted hearing about it. So it obviously happened before that. Okay, so to recap thus far, we have a wild mustard plant that's been turned into kale, collards, cabbage, Brussels sprouts, kohlrabi, and broccoli.
That's sick.
So it's like 6 of the major vegetables we eat are actually all the same plant.
That's
But
nuts.
why stop there?
Right. Why would you stop there?
Right. One of those hundreds of broccoli varieties was further selectively bred to create the nearly pointless plant cauliflower.
Hey, now I like cauliflower.
I personally think, well, I think we got a bit too far with that one, but to each their own. I understand some people, apparently like Victoria,
I
even
don't
find
mind
it edible.
I don't mind cauliflower,
It's
especially if you
it's-
drown it in cheese.
Well, then just have the cheese. Right? All right, anyways, there's even more varieties to this plant that have been made up now, like broccolini and broccoflower and all these weird sort of niche ones. But, we've sort of, I feel like we've maybe maxed out what this plant can do.
I can't think of any other parts.
What about the root? Have we?
The
roots.
Yeah, we do something with the roots. Maybe that'll be the next thing people will start working on.
I guess.
It's got to be one of the strangest and most heavily selectively bred plants on Earth in terms of the variety of end product that we've gotten out of it as far as veg that we eat. I can't think of any other species that we've, as humans, have done more with all the parts of the plant to like selectively breed for those to make it into something that most people would consider different plants.
Yeah,
And
you don't
they're
think of them
not.
as the same.
Yeah.
They think of-
They're all the same plant,
different
just different
things.
varieties. So very cool. I was munching down on some Brussels sprouts, and I was like, I think it's time we talked about this on the show.
I mean, you can wind up with something Kirk likes, like Brussels sprouts, and something Kirk really
Right.
doesn't like cauliflower.
there you go.
Pointless. Utterly pointless. All right. Wonderful. Well, that's what I have. Tell you what, we're going to take a quick break, and then when we come back, it'll be Rachel's turn to regale us with her story. Strange by Nature podcast is brought to you by listeners like you who have joined the Society of Strange, our membership group on over at patreon.com/strangebynature. Society of Strange members can join at one of 3 different membership levels and help support the show and also get some fun stuff like water bottle stickers or access to super secret content. So a thank you to those who have joined already to help make this podcast possible. If you haven't joined yet, we'll see you soon over at the Society of Strange at patreon.com/strangebynature. See you soon.
Welcome back, everyone. So what do you both know about particle accelerators?
Yes.
Oh my! I mean, I know I'm a pretty big nerd. I know the basics, but
Yeah.
My uncle actually is now retired high energy physicist who worked at various particle accelerators over the decades.
Awesome.
So yeah.
Yeah, that's awesome. So obviously there's a couple famous ones. Notably, like the Hadron Collider is one of them. The particle accelerator that I want to talk about today is the National Accelerator Laboratory, and it's now called Fermilab, and it's located in Illinois.
yeah.
Fermilab.
Yeah, it is.
Yes, Fermilab.
Yep.
And I want to talk about the beginning of this particle accelerator, okay? Because there's a few things that happened. So notably, this is in the middle of the space race. This is the late 1960s. They go about and they want to build this 4-mile looped particle accelerator. They get money from Congress. It was $250 million. And that was their budget, and they had to do it within 5 years, okay?
Oh, jeez.
Yeah,
That's not a lot of time.
It was not a lot of time.
Although it was a
not
lot more money
necessarily-
back then.
There
Yeah.
was. That was $250 million in 1960s time was no laughing matter. But
you throw
still,
enough money at something, you can do it a lot faster. Yeah.
it's pretty tight, So, and they had to make sure that everything ran on time, too. They couldn't have any delays. They did end up finishing this accelerator on time and within budget by 1971. Okay?
Wow.
I don't know how, but they did. But when they turned it on, they were able to get the particles going. But once they were tried to get above, I couldn't quite tell what the units were. They couldn't get the speed up past 70 BeV. I'm not sure what that stands for. I tried to look and I couldn't find it.
Probably like billion electron volts or something like that.
Probably, yeah. They tried to get it above
That
like
seems
70.
That seemed like a lot.
It is.
Okay.
They tried to get the speed up past that. The accelerator would fail. And they didn't know what the problem was. They wouldn't continue in that loop. Okay. Which is a problem since, that's the whole point of the accelerator, right?
Right, is to accelerate
the particles.
Particles very quickly, yeah.
So they went through and they tried to figure out what could be going wrong. So what do you think could be going wrong?
There was a rat nesting somewhere in the tunnel.
There was a vibration.
Those are very different answers.
They are very different answers. There was not a rat nesting in the tunnel.
Cute. It's all. Sometimes it's weird things like that.
So so earlier in the project, after being used after a few months, they had to replace some of the magnets because the magnets would shut down. These are like super serious magnets, like several ton magnets to get the particles going. So they had to cut the tube, and when they cut the tube, they accidentally left some metal slivers behind. So what would happen is they would start getting up to speed when the magnets would get powering when the magnets powering the accelerator sped up too much, the slivers would attach themselves to the walls and knock into the particles, and it would cause it to fail. Okay?
Oh, wow. Okay.
So
my answer was closer, in other words.
Your answer was closer.
I mean, a rat might do the same thing, although it wouldn't be magnetized.
I'm going to hold on to the rat thing for just a moment more.
Okay.
Because, this is a 4-mile long collider in a loop. There's a way to, get into it, to loop it around, to, be able to clean it. But how to go about it is the problem. Enter...
How to go about cleaning it?
How to go about cleaning it.
To get the metal fragments out?
Yeah.
Okay, I got you.
To get the metal fragments out.
That is problematic, yeah.
Enter Bob Sheldon. Bob Sheldon.
Okay.
He was an engineer.
I know where this is going.
A project fixer. He was an engineer, but he was the person who was in charge of looking for solutions and trying to make things as cheap as possible. If there was an issue, get the problem to go away as quickly as possible with costing the least amount of money. So if there was a delivery delay or they couldn't get material in time, he would find a cheaper or easier solution. Okay. So of course, everyone was like, oh, we'll go to Bob. Now Bob is from the UK and he came up with a solution because in the UK, he was a hunter and things too. And what they do is they send ferrets down rabbit holes to flush out rabbits. So, why would it not work for flushing out whatever it is, be it metal slivers or anything else in the tunnel? So his solution was to send
hair behind.
His
well,
solution.
ferret hair is not magnetic. So.
No, it is not. Was to send a ferret, which they named Felicia, down the tunnel with cleaning tools attached down the tube.
So there was
I love that.
she had a little brush tutu, basically. We had the same thought, Kirk.
Sort of, yeah.
Sounds so cute.
I've seen pictures of Felicia. She was very cute.
Or maybe like a ruff, like you were talking about, like a neck ruff.
Oh, that would be
Like
good.
you're referring to.
Yeah, like those
on the show
Elizabethan collars, sort of the variation that animals wear. Cone of shame.
Oh. He was a hero.
Well,
or she's a hero.
That would be great, except for the fact that this is a tennis ball sized tube. So if you put a ruff around her neck or anything, she's not going to be able to get through. So what
if
they
it was exactly
did do,
the size of the tube and real fluffy.
Ooh, that would be good.
Yeah, that's kind of what I was thinking of.
So what they did do was they did make her a special collar, but they attached a string to drag a metal cleanser swab around behind her for cleaning this
That's probably better.
tube. Now here's the thing. I know you're wondering, or at least our listeners are probably wondering, what if she poops? That would be an issue.
That's not what I was thinking, but it's a good question.
What would you do if a ferret pooped in your collider, right?
Put a diaper on her.
That is what they did, yeah. They put her in
There
a
you
diaper.
go. Amazing.
So they got Felicia, fun fact, they got Felicia for $35 from a farm in Minnesota.
Woohoo.
And they brought her in, trained her a little bit. But you know what? Felicia just did not want to go down this tube. I don't know why she would want to go down this 4-mile tube. So this was the main ring. Particle accelerators are generally made out of several different rings. So there was a part that was still under construction that wasn't the main ring, but it was in 300-foot sections. So what they did, since this was the vacuum tube, they had her go through those because she eventually was comfortable going through those. And
I'm assuming getting a treat at the end.
Oh, 100%.
Working up to it, basically.
Yeah.
Working up to it. And they eventually got her to go through, and it took her a couple hours to go through these 300-foot tubes because, I mean, they are ferrets, but I would get very just so tired and claustrophobic going through this tube. Yeah. But she did eventually emerge, and she was tired but healthy. So she did this with just about all of the vacuum tubes that were around. And of course, she was doted on by all the physicists and everybody who worked at the lab. They never did, though, put her in the 4-mile long main ring. Another engineer came up with a mechanical version called a magnetic ferret for the main ring. That was more or less it was a bunch of magnets held together, pulled along a steel cable, pushed in with compressed air to pick up the debris as best as it could through the main tube. And eventually they did figure out that one of the issues was the stability of the orbit of the particles, which also caused them to crash into the wall. So it was a couple different things, but this accelerator had a ferret running through its tubes for a while. She went on to be retired, and she was the lab mascot. Unfortunately, Felicia did die in 1972, but she was very much doted upon by everyone who was there. So.
Oh, man. I think that was just slightly before, maybe that was right around the time when I think my uncle started working at Fermilab. I'll have to ask him if he knew Felicia. You will have to ask.
Oh, please. Please do. Well, that's what I have for you both today.
Cool. And I just for our listeners and for our own edification, I did look it up. MEV, the unit of measure. I guessed it was like million electron volts. I was close. It's mega electron volts. And to give you an idea, like we've gone beyond there now because they're now measuring them in either, you got giga electron volts and then tera electron volts and peta electron volts and now exa electron volts.
Oh my
gosh.
Good.
We've gone a bit higher in power since then, but still very cool what they were able to accomplish.
Yeah, it's very awesome. All right. We're going to take a quick break, and when we come back, it'll be Victoria.
Hey, we're back. For our final segment this evening, I have just a light, inconsequential kind of topic to cover. How did life on this planet begin?
Oh, good.
Oh, real light. Yeah.
Right. That's not an existential crisis waiting at all, Victoria.
Let me just check my watch. We got 8 hours left in the show. Go for it.
Yeah. This is going to be, well, so just a sneak preview. This is a topic I chose because I saw a cool article about some recent science, and I was like, oh, this will be fun. And then I realized getting into it that I had to go over the origin of life on Earth. So.
I think I saw that same article, so I'm looking forward to what you talk about next week.
No, I'm just doing, I'm doing that topic this week, but I'll get to it after I.
Okay.
Yeah. Anyway, we can't really know how life began on this planet for sure, since the answer is more than 3.5 billion years in the past.
Yeah, that's a little
Still working
hard.
on that time machine.
Yeah. But to start off with, just a little timeline orientation here. The Earth was formed about 4.6 billion years ago. And the first billion years of its existence or so was characterized by near constant bombardment with large asteroids, which,
kind of a bummer.
Yeah, not an environment super conducive to life on the surface.
Not really.
Yeah. Eventually, around 3.8 billion years ago, the period that was known as the Late Heavy Bombardment, which I just love.
I love that.
Ended.
That's a great name.
Yeah. At that point, collisions became less frequent. And, there's some fossil evidence that life may actually have begun as early as 4.28 billion years ago, so before the end of the Late Heavy Bombardment. But this would have been potentially in hydrothermal vents, which call back way back to an episode where I talked about life at hydrothermal vents. But the idea is these are protected from surface bombardment and not dependent on the sun's energy. So,
makes sense.
Possible candidate there. There's some disagreement, but kind of the earliest fossils that everyone seems to agree on are from about 3.5 billion years ago. And they're called stromatolites.
Yeah.
And they're super cool. They're sedimentary formations that have striped layers that paleontologists have determined were created by multiple layers of cyanobacteria that live in the ocean. And the reason they know is because these are still being made today. There are places on Earth where you can go and look at current stromatolites, not fossil stromatolites.
Yeah.
Yeah, I've got a stromatolite sitting around here somewhere.
Yeah, I saw Kirk moving around.
Seems like the kind of thing I just
Kirk
have, of course.
One.
Yeah.
It's from up in the part of the world where Rachel now resides.
Yes.
I think I had one at one point. I'll let you know if I find any more.
Some very old rocks up there in the Canadian Shield. Anyway, we do know that life started, obviously, and we know approximately when, but there's still a huge amount of debate about how that happened. And part of the problem is that there are a lot of different molecules that need to form to create life as we know it. And some of the most important are DNA and RNA, which you probably know carry genetic information in all life forms on Earth.
Right.
Pretty important.
Yes. And so each molecule of DNA or RNA is a long chain. It's the famous double helix that you've probably heard of. And each unit in the chain is called a nucleotide. And each nucleotide consists of sort of three main parts. One is a sugar, one is a phosphate, and one is called a nucleobase, which is a nitrogen-containing compound. And it comes in 5 different flavors.
Yes. 5 flavors? I just remember 4.
Well,
wait,
DNA.
Because RNA, yes. I'm with you.
DNA has 4 types: adenine, guanine, cytosine, and thymine, but we're just going to get cozy with them and call them A, G, C, and T.
Oh, thank you.
Yes.
Hey.
And RNA has most of the same ones, except that thymine is replaced by uracil. So T becomes a U.
Mm-hmm.
Yeah.
Bringing back all my biology class.
Yes. I had to relearn all this stuff recently.
Mm-hmm.
But anyway, all those 4 or 5 nucleotides in different combinations create the genetic codes of every single living thing on this planet.
Mm-hmm.
Now, DNA seems like a horribly complicated molecule to try to construct without an organism there that has the cellular equipment to construct it. Like, how would it even begin?
Right.
And to try to answer this question, we have to take another step back and talk about where the elements come from, which is stars. All elements except hydrogen and helium are formed by fusion within stars. And then they kind of make their way out to other parts of the universe, the solar systems. And then with the addition of energy, carbon and hydrogen can join and make organic molecules along with other elements. You do need a source of energy for this, but it could come from different sources. So it could come from UV radiation. It could come from impacts, like meteorite impacts. It could come from lightning or other electrical discharges as some examples. Mm-hmm. And some of these conditions could have occurred on early Earth, but they are definitely happening out in space. There's a lot of energy out in space, and there are elements out there. And it's been known since the late 1960s that, in fact, meteorites can harbor amino acids, which are the building blocks for proteins. And around the same time in the late 60s, it was discovered that the nucleobases, not the whole nucleotides, but nucleobases A and G were also found in meteorites.
Huh.
Very cool.
So that's been known for a while. But the recent discovery that prompted me to pick this topic was that scientists believe that they have now discovered all of the other remaining nucleobases in meteorites. So all 5 of them have now arguably been shown to be present in space.
Wow.
And in addition, ribose, which is a sugar that's needed for DNA construction, has also been found in meteorites. So that's getting sweet. Like a lot. Well, sugar is sweet.
Oh. Oh boy.
That was good. Solid, Victoria. I like it.
Yeah. So, in one sense, all of the stories about aliens being the possible source of life on Earth could be kind of true.
Mm-hmm.
Sure. There's a bit of a caveat here, which is that the technique that was used to show these recent discoveries was basically doing an extremely delicate chemical analysis of material from meteorites that have fallen to Earth, right?
And they have fallen to Earth being the key phrase?
They have fallen to Earth, yes, exactly.
Yeah.
So it's this very sensitive chemical analysis, and then they're comparing material found on the meteorite versus material that's in the soil near the meteorite.
Mm-hmm.
Okay. And comparing the abundance of different compounds in those 2 samples. And so, for example, if uracil, showed up in greater abundance in the meteorite sample than the soil sample, they concluded that it came with the meteorite and wasn't somehow contaminated from uracil that had an Earth origin, right?
Okay.
So, it's suggestive. It's not conclusive.
Mm-hmm.
Obviously, this method can never really be a slam dunk. To really resolve this issue, we need to go probe some asteroids, which luckily has been happening.
Yay!
Yeah. This was really a Japanese team that published this study recently, and a Japanese probe actually sampled an asteroid and came back to Earth in 2020. And the samples are being tested, so results may be coming soonish. And a NASA probe is expected to return in September 2023 from a different asteroid. And just to be clear, asteroids, when they fall to Earth, become meteorites. So that's the connection. So
I'm very excited.
We may find out more soon. But, life could have sort of come from outer space. Or at least part of the chemical components of life.
Mm-hmm.
That's so cool, though.
Yeah.
I love new things being discovered.
I know. Plus,
That's
space
why
is
we do
cool.
this.
That's true. That is why we do this.
Yeah, that's what I have on that for you guys today.
We'll put a note in the file that you will be doing an update on this one in the future when we get samples back, because I'm excited to hear what they find out.
I want to know. Yes.
All right.
All right.
Well, that's it for today.
Thanks, everyone.
Great talking to you. See you next week.
See ya. Bye.
Bye.
Thanks everyone for listening to today's show. Be sure to subscribe. New episodes drop every Wednesday, and we love sharing this strange world with all of our listeners. If you would be so kind as to leave us a 5-star review, that would be great. It lets other lovers of the strange discover the show. You can reach out to us on social media by searching for Strange by Nature Podcast on Twitter, Facebook, and Instagram. You can send us an email as well. Our address is contact@strangebynaturepodcast.com. If you want more information about the show, you can also check out our website, which is strangebynaturepodcast.com. Until next week, get outside, stay curious, and embrace the strange.